All right, so today I'm just going to review what we talked about last time with respect to deriving transfer functions, and then we'll go into look at using transfer functions to assess the stability of a process. So just as a quick review, so for transfer functions, again, we start with the general process model, and a general process model could look something like, we could have, so last time we said something like, we have a constant times the derivative of temperature with respect to time. Could be like a constant times a T in, and this T in could be our input, maybe plus another constant times temperature. And again, this temperature is our output plus another constant. So here I'm just sort of giving a general just a general equation for this, what would be a process model. And so a transfer function is a function that relates in the Laplace domain the input to the output. So a transfer function for a process is in the Laplace domain, and it's going to tell us the relationship between the output. And for a process, the output's going to be the control variable, which is the variable we care about in the Laplace domain, divided by the input, which would be the input parameter, the function in the Laplace domain. Okay, so this transfer function, what this means is it means that the input, like the function of the input, doesn't matter with respect to the transfer function. But the transfer function for a process, it's going to be what it is. It's going to be derived from the overall process model, and it's going to tell us how the output changes with respect to the input. So for example, the input could be something like a ramp, so the temperature could slowly increase. And then based on this function, we can determine what the temperature is going to do. The input could be a step function, so we could see a step function change. It could be a sinusoidal input. Could be a variety of things. But this transfer function is irrespective of the input to the process. Okay, I'm not going to go through in detail, but just to remind, the important things about this is that this is in terms of deviation variable. And so essentially what this means is it's different. It's the difference from like the steady state, or it could be like the initial steady state condition. So a process is operating here, and then there's some sort of change. An input to the process is staying here, and the process is staying here. There's a change in the input, and it tells us how the output process responds to that input change. Okay, so it's in terms of deviation variable. So general process that we use here, again, we essentially defined the variables with respect to deviation variables. So we define variables in deviation variable. The second step that we did, so we put things, so again, we represented, step 0, maybe I'll say, is we derived the process model. So we need to know what the process model is. So what is the model that relates the input parameter to the output? Then we defined all the variables in terms of deviation variables, which is the difference from their steady state value. The next thing we did is we wrote and subtracted out the steady state condition. And again, the previous slides that we did are shown here. And so just kind of going back to the beginning, we defined the process model, wrote deviation variables. We subtracted the initial steady state condition, took the Laplace, and then came up with the transfer function. Okay, so that's what we're doing. So deviation variables. So then the next step is define and subtract the steady state or initial condition. And again, when we did this, when we defined and subtracted the steady state conditions, what we did is essentially we converted all the variables to deviation variables, and all the constants were removed. The next thing we took the Laplace, and then finally we solved for G of S. Okay, so that's the overall process. And again, you can review this what we did last time. There is another way to come up with the transfer functions. And if I've already lost you, come back. because this is extremely important. If you have to come up with a transfer function, there is an easy way to do it. And the easy way to do it is equation 5.7.3 from the textbook. And what this equation says is that the transfer function for a process, and the good news about this, okay, and I'll also say this equation can be applied to any process model. It can be linear or nonlinear, it doesn't matter. This equation will be valid because it will linearize any nonlinear terms. Okay, so the transfer function, which tells us y of s, which is output, over u of s. Okay, so this is going to be the partial derivative of the function with respect to the two variables, output versus input. So the partial with respect to the input. Okay, so take the partial derivative and then you evaluate it at the initial condition, divided by s minus the partial of the function, same function. It has output and input with respect to the output variable, also applied at the initial condition. Okay, so this is the definition that we can use to derive. And so the important thing to note here is that the function, we have to write our function when we apply this method as we have to have a function that's written this way, dy dt. Okay, so this is what this means. All right, if we go back and we look at the last one, right, here's our process, and we're going to apply it to this. We're going to apply it to this case right here. Okay, so what I need to do is I need to write my function. So this is a function of t and tn. So my function of t, which is the output, tn, which is the input, equals dt dt, right? And this equals, right, what I have to do in order to get it to be that is I have to divide all of these things by a, right? So now I have this expressed in this term. So this is going to be b over a times tn. It's going to be c over a t plus d over a. All right? Now once we get here, it's actually, okay, I know people don't like it when I say pretty easy, but what you'll see is this actually is pretty easy. So to take the partial of this function right here. So up here, so d, the partial of the function with respect to the input, which is tn, is going to be, okay, so now g of s equals the partial of this function with respect to the input. So this is the only term that has the input in it. Okay, so the partial with respect to the input is just b over a. The rest of these terms, the derivative is 0 with respect to tn. And then I evaluate this at this term, and it's just the constant. Divided by the partial of this, so the partial of this function with respect to the output, so these terms are 0, so, or this is going to be s minus partial with respect to the output, which is c over a. Okay, so this right here tells us the transfer function for this process. Now, going forward a little bit, the definition, again, the definition of the standard form of the transfer function has these terms equal to 1. So we can go ahead and rewrite these if we want, or we can rearrange this a little bit and multiply everything through by a over c. So if I multiply everything through by a over c, well, I'll just leave it like this. We don't have to go. We'll do standard form in a little bit. But in any case, equation 5.7.3. This is what you need to do. Now, notice that we didn't really evaluate anything at these inputs. You might actually have to do that though if I have like a nonlinear term. So let's just say, for example, okay, if this function were something like plus t times tn, right? If I take the partial of t times tn with respect to tn, that would just be t. t evaluated at the steady state condition would just be t naught or t hat. Okay, so then there would be a t hat term in there. But I was just kind of showing that for example. All right, are there questions on that? Because this is, you'll have maybe a problem or two that you can do, and if something like this shows up on the test, you actually have to derive a transfer function that's sort of a more difficult or a more complex equation, that especially one that has nonlinear terms. We can use this. Now, we will also, at the end of the lecture today, we'll talk about how to linearize a nonlinear term. But again, if we use this method, we don't have to worry about that. Okay, so now I'm going to go forward, and we're going to now talk about the stability of transfer functions. So we can determine the dynamic behavior of a process and the stability. So there's two different things we're going to talk about. So the stability is just a matter of whether or not the process is stable. What a stable process means is that if I make a change to the input, I know the process is going to change and reach a new steady state condition. That's, it's going to decay to something that's a new steady state condition. If the process is not stable, what's going to happen is you apply a change in an input, and the output parameter is going to maybe exponentially grow, or it's going to become unbound. So this could be something like a runaway reaction, for example. When we talk about dynamic response, what dynamic response means is characteristics such as exponential decay, sinusoidal behavior. So we can determine whether or not a process has oscillations, whether or not it has decay or growth based on some of these terms. So again, when we use the transfer function to assess dynamic behavior and stability, we want to talk about, just yes, no, is the process stable? And we also want to be able to talk about, are there oscillations or not, or to what extent the process has oscillations. Shown here is a general form of the transfer function. So again, this right here is a general form, or gives us a couple different terms in a transfer function. Now, this could come from a much bigger polynomial that we have factored out and got it to this point. And so this gives more or less some general type of terms that can show up in the denominator. So again, last time when we did partial fraction separation, we showed these, we can kind of separate polynomials into the individual roots. Okay, so these terms that show up in the denominator, these could be the roots. So we can talk about this term right here. A as being like a value that would be like a root of the polynomial of the denominator, which are also called, or they're also called poles of a transfer function. So for example, a pole of a transfer function would be a value that makes the transfer function go to infinity. So if we look at this, we can see, well, if s equals negative a, this would give us a zero term, 1 over 0, the transfer function would go to infinity. So s equals negative a is what's called a pole. And you can also see that s equals negative a is the root of the polynomial of the denominator of the transfer function. So you can talk about those two things synonymously. Okay, we know we can go from here to here. So we can go from here to here by doing something like partial fraction separation, or we can use something that's called the Heaviside method. And this will be something that maybe next time, maybe tomorrow, I'll do an example of that just to kind of show you how that works. And if you believe me for a second that this function can go to something that looks like this, because we can just, we can essentially multiply the top and bottom by these other terms and then group everything together to get back up here. We need to do this. So we need to do this step because for this thing right here, I cannot take the inverse Laplace of this function as it's written here. But what I can do is I can take the inverse Laplace of all of these individual terms because these look like terms that are in the table. So again, here's the function in the Laplace domain. What we're doing here is, again, we're just looking at the generic form. If I take the inverse Laplace of this term, a over s plus a, the inverse Laplace of a over s plus a right, or the inverse Laplace of 1 over s plus a is going to give us this exponential decay term right here. So again, for example, if I had something that was, again, we could pull up the Laplace. If you have the Laplace table handy, maybe you can look at the Laplace table. I'm actually going to pull that up from my book right here so I can just make an example. So if we have something that a term from the Laplace table will look like this. Well, actually, yeah, the exact term is if we have 1 over s plus a in the Laplace domain, in the time domain, this looks like e to the negative at. Okay, so this is the function in the time domain, and this is the function in the Laplace domain. So I know if I get a function that looks like a over s plus a, and I take the inverse Laplace of this, it's going to be this. Okay, same over here. So the inverse Laplace of something that's s minus a is going to look like this. Now this term in the middle, it's a little bit tougher, but again, we're going to work through this in just a second. If I take the inverse Laplace of this term right here, maybe just take my word for it right now, it'll look something like an exponential term times a sine term. Okay, and now this, depending on the value, right? So now if we look at this term right here, okay? If I have an s plus a, inverse Laplace is always going to give me exponential decay, right? So this right here is going to always be exponential decay, which means this term right here is stable. If I have an s minus 5 or s minus 2, if I have an s minus term in the denominator, this is going to give me an exponential growth term. Okay, so if this is exponential growth, this term is not going to be stable. Okay, and then for this term in the middle, it's going to depend on what are the relative values of b versus c, and that's what we'll look at here to see whether or not this term right here is stable. Okay, so if this is stable, right, if this is exponential decay, and this is also maybe a sinusoidal decay, and this is exponential growth, the whole function will be unstable because these terms will go to 0, but one term will grow, which make the whole function grow. So it just takes one term being unstable to make the entire transfer function unstable. So in general, we can see that if we have something that looks like this, if we can separate the fraction and we have a term show up that's an s minus something, we know that that's going to be an unstable transfer function. If we have something that shows where we have these essentially this quadratic form that has imaginary roots. So if we have a quadratic form with imaginary roots, that's going to indicate we have some sort of dynamic behavior. Okay, so that's going to be very general. So I'm going to pause here for a second and give myself an extra page or two. Okay, so I want to go and kind of look at, what is the stability? What is the stability based on those terms right there? And to do that, I'm going to do a little bit of derivation, and I'm going to kind of talk you through it a little bit, and we'll look at it, and then I'll give you this information on Canvas. So, like I said, in general, we have this transfer function, and the transfer function is defined as the output over the input, right? So y is a generic term for the output, so that could be temperature. U is a generic term for the input, so that could be flow. We can also express this, this is a function in the Laplace domain. Okay, so once we have the transfer function, at some point, we don't necessarily have to treat it this way. We can say very generically, this is equal to the numerator in the Laplace domain over the denominator in the Laplace domain. So the denominator in the Laplace domain is what's going to determine the dynamic behavior and the stability. The numerator can just say whether or not it goes to 0 or exhibits some other type of behavior. Okay, and so this could be, essentially, we can write this as ns numerator all over some sort of polynomial. And if we have a polynomial, we can generally factor out the polynomial. And I'm going to factor out, for this case, for this example that I do, I'm going to factor out the polynomial to look like s plus a over s squared plus BS plus C. Now notice in here, I'm actually ignoring that S minus D term, because this is kind of gives us a generic term for that. So we can express S minus A and S plus A sort of the same way. So in other words, if this A term is positive, we know this is going to be stable from the inverse. And if this term is negative, it's going to be unstable, like what we just showed. Okay, so again, if we want to, again, we're looking at this right here. We're looking at the transfer function and the general behavior that relates the output to the input. If we wanted to actually calculate the dynamic response, so if we actually wanted to go to get to something like y of t, right? We can use the transfer function. So the output response would be the transfer function multiplied by the input function. So to do this, we would have to have an actual function for the input. So for example, we could say, well, we want to sketch the dynamic response to a step change in the input. So last time we looked at a step change in an input would be something like y1 over s. So this would be g of s, the transfer function, times, maybe we said the step over s. So this would be the input function in the Laplace domain, which would essentially be taking this term right here multiplied by 1 over s. We don't need to worry about this function right here when we look at the overall stability, because this term right here is essentially in the time domain represents a constant, and a constant is always stable. And this kind of tells us why we don't need, as long as the input is bound, we can determine what the overall stability is by just looking at this transfer function right here. The good news of this is that we don't actually have to go through all of the math to calculate this. So I don't have to take this, multiply by A of S, do the partial fraction separation, go through, rearrange, separate it out, take the inverse Laplace, get y of t, you see where I'm getting. So we don't actually have to do this to get stability. We can just use this right here to get stability and the dynamic behavior. Right, and so that's kind of what we care. We don't care about the exact numbers. We just want to know generally how do we think this process is going to respond if we know this information. And then again, we can get the transfer function. So we talked about we can get the transfer function from deriving it from the process models. And later, we're going to get the transfer function from actually experimental data or process data. So we can use process data to back predict what the transfer function is for a process. And then we can assess the dynamic behavior. And then that's something that may be more useful. Then when we add the controller to the process, it's going to kind of make things a little bit more interesting and have some different type of behavior. All right, so that was a lot of words to kind of set up where we're going. So now I want to talk about the stability of this thing right here. So actually, I think what I did in my notes is I did say, I'll just keep it this way. So I'm going to call this A times NS over S plus A, just to kind of get the whole story here, BS plus C. So this is overall what YS would be. And so again, if we want to get this in the time domain, we have to take the inverse Laplace. And to take the inverse Laplace, we first have to separate this out. And so this is going to look like something like C0 over S plus C1 over S plus A plus C2 over S squared plus BS plus C. Now these terms could have S's in there or not. It doesn't necessarily matter for what we're looking at. We just care about these. So first, I guess if you want to stop me, you can see how we can do like a partial fraction, or we can use a method to to separate out this equation into these individual ones. Actually, what I didn't, I got a little bit ahead of myself. I'm still calling, this is still Y in the S domain. Once we have Y in the S domain that's in this form, we can now get Y in the T domain, right? And so to do that, we can actually just use the table. So we can take the inverse Laplace of 1 over S, we can take the inverse Laplace of this, and we can take the inverse Laplace of this. Okay, so the inverse Laplace of this right here, I'm going to write these in, we're going to do a couple terms. So first term, second term, third term. When we look at the first term, if I take the inverse Laplace of this, the inverse Laplace of C over S is just going to be, so the inverse Laplace of C naught over S is just going to be C naught. So this is going to be a constant, which is always going to be stable. So we don't have to worry about this term. If we look at the second term, inverse Laplace of C1 over S plus A is going to be C1 exp, just like what we just looked at, A of t. So we can see now here that if A is a positive number, this is going to be stable. If A is a negative number, this is going to be unstable. But in any case, a term that looks like this is either going to be exponential decay or it's going to be exponential growth. Those are the only two choices. There's going to be no dynamic behavior, or there's going to be no like oscillations or like squiggles in the data. And now we'll look at the third scenario. It's a little bit tougher. And so maybe I'm going to go to the next slide. So the third term is going to look like this. C2 over S squared plus BS plus C. So I'm going to do a little bit of math right here, and I'm sort of doing it in my head. I actually already did the math, but I'll show you the result of the math, and then we'll go forward. Okay. I can express this as C2 over, this is going to be S plus B minus square root of B squared minus 4AC over 2. And then S plus B plus, let's see, S plus B plus square root B squared minus 4AC over 2. And so what I did here, and maybe you can sort of, maybe you can see a little bit, is these right here, this term right here, and this term right here are the roots. So we know that the roots of the quadratic equation would be S equals, what is it? S equals negative B plus minus square root B squared minus 4AC over 2A. But actually in this case, I used different word, or there A is equal to 1 right here. So this was equal to, there was no A right here and no A up here. And so I just wrote this as the poles in here, right? So we can express this way. And now depending on the relative values of these terms, we can have different things. So we have essentially 3 scenarios. So we have 3 scenarios here. Now I'm doing a little bit of math right here, and I guess I'll throw it out there that, this isn't necessarily something that, we'll have to go through in a lot of detail later. But I want you to see how, I want you to see why we can determine what the stability is based on the relative values of these. And that's essentially what we're looking at. Okay, so case 1 is we have if. So for case 1, we can say B squared minus 4C is greater than 0. So if B squared minus 4C is greater than 0, so this term is greater than 0, right? That means we have a positive value in here. This means we have real roots. Okay, so if we have real roots, so if we have real roots for both of these, right, then it's going to depend on what's the relative value of these. So we can say now if C is greater than 0, okay, so if we look at, first of all, we can see that B in itself, so the first thing is if it's real roots, B has to be greater than 0. If B is less than 0, then these terms right here are going to be negative. So this term right here will be negative if b is less than 0. Okay, we said last time. So if c is greater than 0, this is going to be stable. And the reason why it's stable is because this term in the square root is less than b. And so therefore, I'm going to have an s plus a term. This is going to give me an s plus p term. And then the inverse Laplace of this s plus p term is going to be exponent of negative pt if c is greater than 0. If c is less than 0, it's going to be unstable. And the reason why it's unstable is that this term right here becomes bigger. And so it's going to give me, in the denominator, it's going to give me this s minus p term. And if I have an s minus p term in the denominator, so an s minus p term in the denominator is going to give me an exponent to the p times t term when I take the inverse Laplace. So that's why this would be unstable. So the point here is that anytime, if c is 0, regardless of what b is, it'll give me this s minus term in the denominator, and that's going to be unstable. Okay? If we have real roots and if c is greater than 0, it's going to be stable. Okay, so as long as b is greater, so b has to be greater than 0 for it to be stable, and then also c has to be greater than 0 for it to be stable for that condition. Okay, so that was one scenario, and that's the trickiest one to go through. A second scenario could be if b squared minus 4c equals 0. Okay, so if this term inside here is equal to 0, right, then what I have is repeated roots. Right, so b squared minus 4ac is 0, so I'm going to have an s plus b over 2, s plus b over 2. If I have repeated roots, right, all that matters is the value of b. So if I have repeated roots, then if b is greater than 0, it's stable. Therefore, if b is less than 0, these are going to give us s minus b over 2 terms. It'll be unstable. Okay, and then finally, the last condition is going to be if b squared minus 4c is less than 0, then we're going to have imaginary roots. If b, so again, if b squared minus 4c is less than 0, it's going to give us imaginary roots. If we have imaginary roots for this term, what that's going to mean is that there's going to be oscillations. Okay, so we know now if we have imaginary roots in this term, the dynamics of the process will have oscillations, because it means that there's going to have to be some sort of sine root to the system. Okay, so we still need to decide the stability if there's imaginary roots. So, but I don't know. Let's look at this, and let's just say if there's imaginary roots. If there's imaginary roots, this is going to be a s plus. We're still going to have this b term. We're going to have a b minus some imaginary term. And so if we have imaginary roots, right, these terms right here, they're not going to contribute to the positivity, or they're not going to contribute to the value of the real term, which determines the stability. Therefore, the same thing as if b is greater than 0, it's going to be stable. Okay, so essentially the bottom line is that if we go back and we look at this form of the transfer function right here, right, if we can express the transfer function this way, if all of these terms are positive, if all of the roots are positive, it's stable. If one of the roots is negative, then it's unstable. So all we have to do is just make sure we have all positive roots. And that's what can determine whether or not it's stable. If there's imaginary roots, there's oscillations. Later, we're going to be able to see there's other ways we can determine the degree of the oscillations fairly easily. I want to show one last aspect of this. And to do this, I'm going to go ahead and add one more page. And so we said I'm going to look at this. We said the condition where we're looking at b squared minus 4c is less than 0, and this means it has imaginary roots. And if it has imaginary roots, we can go ahead and look at again, we're still looking at this term in the bottom was s squared plus bs plus c. I'm just writing it over there. So if this term has imaginary roots, so here's the quadratic equation, the solution is imaginary, we know this is going to give us imaginary behavior. We have to still make this term right here look like something that looks out of the table, and so we have to do a little bit of work. What I'm going to do here is I'm going to do what's called completing the square. So add a b squared over 4, and I'm going to subtract a b squared over 4. Right, this is something we can do. I'm just adding 2 terms and I'm not changing it. If this is the case right here, again, now we do the whole completing the square. This is going to give us s plus b over 2 squared plus square root of c minus b squared over 4 squared. Right, this term right here, these terms in here it's just a constant, right? So what I have here is I have an s plus b over 2 squared, that's a constant, or no, I have this s plus a constant squared plus a constant squared. This doesn't exactly look like something that looks from the table, but what I can also do is to make it look like something that looks in the table, I need to have whatever this constant squared looks something like this, c minus b squared over 4. And then since I multiplied that in the numerator, I also have to put that in the denominator, c minus b squared over 4. Again, this right here, it's just a constant. And so really I should write it out in front of here because the table has this term right here. And so from the table, actually this minus the C2. So I'll put the C term, move the C2 term out of here. The table has something that looks like omega over s plus a squared plus omega squared. And so again, this is the function in the Laplace domain. And the function in the time domain for this is going to look like sine omega t exp negative at. We don't need this. So this is the function in the Laplace domain. This is the function in the time domain. So again, I had to do completing the square to make this term look like an s plus a squared and then plus a constant squared. And if this is the case, then I can convert between these two, and then I just have this constant out in front. Right, so therefore, again, going back, if this has imaginary roots, we know that it's going to have oscillations because it's imaginary roots. The dynamics of that are oscillation, or some sort of like squiggly functions, because imaginary comes from sine. To show that it has this form, we do this. We completed the square. We did a little bit of math, reorganized, and then we can again take this function right here and now make this function look like in the time domain. The initial function that we have in the time domain is going to be, again, take the inverse Laplace of this function to give us the time domain is going to equal c over 2 square root c minus b squared over 4, because again, we put this in the denominator. And then we had exponent of negative b over 2, because this was our a term, times t, times sine. Our omega term is this term right here, whatever the square term. So it's going to be sine of c minus b squared over 4 times t. And all of that is in the sine. So this would be the inverse Laplace in the time domain of this function that has imaginary roots. And it's always going to look like that if it has imaginary roots from that form. right, so this shows, again, if B is positive, as long as B is positive, this is going to be exponential decay. The relative value of C in this case doesn't really matter, but we know that C has to be, if B is positive, in order for this to be less than 0, C has to be positive for this to have imaginary roots. All right, so that was a lot of work, a lot of math. Kind of got stuck, tied up a little bit in some circular stuff for a minute, so, but just wanted to go through that and show you how that works. So some of these slides just show us other ways of plotting. Some of these things aren't necessarily that important, but they're talked about in the book, and I wanted to show them on the slides to have them here. So we can plot the poles. So if we know the poles of the transfer function, we can plot them to determine whether or not what the dynamic behavior and the stability. And this is called a root locus type plot. We can plot real versus imaginary roots. So again, if we have two real roots that are negative, everything that shows up over here is going to be stability. It's going to be stable. So what shows up on the if the real roots, so real roots are negative, it's stable. If real roots are positive, it's going to be unstable. If you have any imaginary roots, again, if they're imaginary roots, it's going to be plus or minus. It's going to determine anything up here. It's going to have oscillation. Okay, just a quick reminder right here. So we said negative roots are stable. What I mean by negative roots is, again, if we have something like s plus a, the root for this, right, the root is s equals negative a. Right, so the real root part of this is, if it's negative, it's stable. If it's positive, it's unstable, because if it's positive, right, if the root's positive, this would be a 1 over s minus a, and then the root would be s equals a. So if this is positive, it has this form. Inverse Laplace of this form is exponent of at. This is exponential growth, which means it's not stable. All right, so that's kind of the point of that. These plots aren't terribly useful. Other ways, so again, we're looking at, this is the imaginary, real versus imaginary plot. If this is what the root looks like, if this is what the root looks like in the, so again, this is transfer function. We're kind of comparing the roots of the denominator of the transfer function, and this is the dynamic response, the dynamic behavior in the time domain. Remember, so transfer function is Laplace domain, function is in the time domain, and again, we know this because of what we just talked about. This is exponential decay. Again, if this right here, so again, now if we look at here, here's the roots right here. So what we can see is that in this case, we have real negative roots. So real negative roots, which give exponential decay, but we also have oscillation. So this would be something that looks like, this would be like a sine times an exponential decay. And if we have, again, a sine function looks like this, exponential decay looks like this. So if we multiply sine by exponential decay, we get the function that's shown here, right? So again, this is going to be stable, but it's going to have oscillations. The faster the exponential decay, the faster this is going to settle out. The larger the amplitude on here, the larger the kind of oscillations. And again, you can look at the frequency. You can look at the omega term to determine like how long these oscillations are going to be in between there. If we have roots that show up here, so again, we have positive roots. If we have positive roots and imaginary roots, it's going to be exponential growth for the same reason. And again, just as a quick summary, if the process is unstable, that means it grows when there's any sort of change in the input. So any change in the input, whether it's finite or a bound change in the input, is going to cause an unbound change in the output. If you have a stable process, an unbound change in the input can still lead to an unbound change in the output. And again, the example here is a runaway reactor. So in general, if we have something that's S plus A, right, this is going to look like stable. If we have something that's s minus a, right, a term that's this is going to be unstable. And if it's a quadratic, we just have to look a little bit closer at it. If we have a graphical representation of the roots, then again, we can just use the information we just talked about. Okay, so my question right here is what kind of dynamic behavior would you expect if we had a real root equals 0, but just imaginary roots? So again, thinking about mathematically what this represents. So no real root, just imaginary root. This is an indication of sine. This would be like a sine omega t type characteristic in the time domain. Sine omega t in the time domain. Again, if we remember the roots we're looking at here, Laplace domain transfer function, we're using knowledge of these roots to suggest what the behavior looks like in the time domain. In the time domain for something like this, it's just going to look like sustained oscillations. This is still considered to be stable, but the specific indication of what this roots represent is it would be sustained oscillations. As we made a change to the input, the process is just going to continue to oscillate. Okay, there's another way we can assess stability if we have a big polynomial. And I'll say for this class, we are not going to treat polynomials that are bigger than third order. So third order polynomial might be the biggest we do. But again, you can use, again, if you're familiar with this, you can use the Routh array, Routh stability criteria to determine the stability of a transfer function. And there's a definition for it. And it's going to kind of follow the same thing that we talk about here for a third order. So we already know for a second order, or if it's a first order function, right? So a first order polynomial would just be something like s plus a. Now remember that we're talking here strictly about the denominator of the transfer function. So if the denominator of the transfer function were s plus a, right, this is first order, we know what it's going to be stable. If it's second order, we also looked at for a second order, we just said all of the terms had to be positive. So if it's third order now, we have to factor out a term. So this is going to be, so we're going to treat this as, let's say, overall, we're going to do third order for this. If you have a polynomial that's third order, from your math classes, again, if we can plot a third order polynomial, a third order polynomial will always have at least one real root, right? So again, if we have a second order polynomial, a second order polynomial could look like this and never go through this, never have zeros on the x-axis. So this doesn't have to have real roots. But a third order will always have something that goes through. It could have 3 real roots, or it could have 1 real root. Those are the only 2 choices. You can't have just 2, right? It'll look something like this because one of these tails is going to go through the x-axis. So what we could do is if we had a third order, we could factor out that, we could plot it, we could figure out what this root was, and we could factor out this root from the polynomial doing maybe polynomial division. And then we could see what we have left over for our quadratic, and then we could inspect the quadratic to determine what's the dynamic behavior of the quadratic. Sounds like a lot of work, I know. But instead, we can use the Routh array criteria, which kind of mathematically goes through that process and has defined it into this sort of system. So what the Routh array criteria for a third order system mean, what it says is that if all of these terms are positive, then it's going to be stable. All of the terms have to be positive for it to be stable. If A3 and A2 are both negative, like if all of the terms are negative, like if we go back here, we would make sure that this first term is a positive term, because if it's a negative term, we just divide or multiply through by the negative on top and bottom to make this first term positive. We can do that. Okay. Again, so once we do that, if all of these terms are positive, then it's stable. If one of these terms is negative, then it's not stable. Right, so you can just visually look at A3 and A2 and A0, like from here, right? So is this positive, 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 check, 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 okay? If one of those is negative, you can stop there. If all of them are negative, factor out a negative from top and bottom, and then look at the other term. And then all we have to do is look at this term right here. A2 minus A1 over A3 minus A0 over A2. We calculate this term if it's negative. So this is going to be the only one that might trip you up a little bit that you have to do a calculation. That's all I'm going to say on that, because really it's just a plug and chug to determine whether or not it's stable. Here's an example that shows an example of a transfer function, right? You can't tell, but what we can see is this is positive, this is positive, this is positive. And so now we need to look at the ratio of all of these terms to see, and therefore we'll see that if we actually do the math on this third term, we'll see that it's actually unstable, even though it looks like from this case right here, all of these terms are positive. The zeros of the transfer function. So again, we talked about the dynamics, which is the denominator. The zeros of the transfer function are the values on the top. So it would be like these values. What are the values of S that make this 0? Those would be what's called the zeros. They can tell you a little bit about the process behavior, but they're not as definitive and not necessarily as useful. So it says if there is, and there doesn't necessarily have to be any zeros. You might have just a constant up top. But what you can get, if you do have zeros, you can get some information. So if any zero is positive, then the process will be, the response will be inverse. What this means is that if the response is inverse, if we make a change to the process, and here's it starting right here, if we know the steady state change will eventually be an increase in temperature, but the transfer function has a 0, what it means is that it'll have an inverse response. It'll initially decrease, and then it'll increase. Right? This is good to know because you might make a change to your process and you're like, wait a minute, something's wrong. It's going the wrong way, and then stop it. But you'll know based on what the transfer function is that it's going to initially respond that way and recover the opposite way. If all of the zeros are negative, then the process can have overshoot. And what overshoot means is that if we know that this is going to be the final steady state of the process, then the process can overshoot and then come back down. Okay, so that's some information that you can get from the zeros of the transfer function. Okay, a couple more things that want to just, I want to talk about a couple things, and then we'll just go through these quickly and maybe try to get wrapped up for the day. One of the useful things about transfer functions is they tell us how inputs are related to outputs, so we can kind of combine these together to get overall process inputs and overall process outputs. If we have a process that goes like a sequence of actuator, process, sensor, we know output from the input, and then the output from the first process is the input to the next process. It gives us an output, that's an input, gives us an output. We can use that information to determine the transfer function for larger overall processes. And so we're going to look at the case right here of this mixer system that we've talked about in general. And so if we have a first order heater, and I'll just introduce a couple things, and these are maybe things that I'm familiar with because I've done this a lot. If I have a first order actuator, like a flow actuator or a flow process, I know that the transfer function for a first order process is going to look like this, tau h 1 over tau hs plus 1. The reason why is this is the standard form for the transfer function for a first order process with a gain equal to 1. So the gain is going to show up in the numerator. This right here is the gain. For an actuator, if I specify for a heater that's an actuator, if I specify an increase in temperature of 5 degrees, then my actuator needs to increase by 5 degrees. So that's indicative of a gain of 1. This term right here is the time constant. This is the rate, how fast it changes, times s plus 1. And this all comes from, if we take a first order differential equation, first order ordinary differential equation, and we go through the process of deriving a transfer function, we will get this form. Any first order process is going to have this form. This is the time constant. Okay, so we derived previously the transfer function for a mixing process. So the transfer function for a mixing process, we showed that it looks like something like 1 to the flows over m times s plus f1 plus f2. Now this is not standard form, so this is something that we derived. So again, we derived it for our process. We know this for the actuator because it's standard form, and now we're told that the transfer function for a first order sensor, because again, it's a first order sensor, I know that for a first order transfer function, it's gain over tau s plus 1. but I know that a transfer function, the gain has to be 1. So this is going to be 1 over tau s plus 1. Okay? These are the overall transfer functions for 3 different processes. In this case, so again, if we go ahead and we want to look at, we have our input right here is, in this case, we have T specified. This goes to our actuator. Coming out of our actuator is, or T1 specified, coming out of our actuator is T1. T1 is going to affect our process. The input to the process is T1, the output is T. T becomes the input to the sensor. The output of the sensor is TS, right? In other words, the overall transfer function that relates, the overall transfer function, so we're saying G overall is going to be the overall output, which is TS, over the overall input, which is T1 specified. Because we want to know if we make a change to this specified temperature coming in, how does that affect what we can actually see? And we know that this is true because GA, right, this transfer function right here, GA, equals T1 over T1 specified. GP is going to be T over T1. And these are all in Laplace domain. Just put the S on there. And then GS is going to be TS over T in the Laplace domain. Right, so if I look at these cancel out, these cancel, and then this gives us TS over T1 specified. So what this means is that if I have these types of sequential processes where the output of one process is the input to the next process, I can combine the transfer functions by just multiplying them all by each other. Okay, so what this gives us here is now we have an overall transfer function is a product of these individual first order transfer functions. So now here we have a third overall. All right, so now you can see how when we start looking at transfer functions for bigger processes, we can go from first order to second order to third order, combine them all together. A couple of things is like once we combine them together, I don't want to necessarily multiply this through and make it, I don't know, simplify it, quote unquote. I want to keep it in this form because again, I can look at this and I can see, well, this is first order because this is positive, this part's stable. This is first order, positive, it's stable. This is first order. These terms are going to be positive, therefore it's going to be stable. If I multiply all stable first order functions by each other, the third order is also going to be stable because I can't essentially create net or imaginary roots from multiplication of first order processes. Because then they just continue to have real roots. The block flow diagrams can tell us ways of combining transfer functions together. For the sake of time for now, I'm not going to go through this math, but what I'll ask you to do is maybe you can kind of go back and look at you can look at this. So essentially for this, we might want to derive a transfer function for this overall process that relates the output, which is CS, over the input, which is ES. Okay, the way that I would do this, or the way that I do this, and kind of have it like this in my notes is, I'm adding two functions together. To get CS, CS is going to be the addition of this function right here. I don't know what this is yet. I'm just going to call this A, and I'm going to call this right here B. So C is going to be A plus B. So now this term B right here is going to come from these overall processes. So again, it's going to be this transfer function, because this transfer function tells us the output of here, which is B, over the input, which is E. So then B becomes, in this case, KC. So B, this function right here, equals this transfer function times the input, right? Because this transfer function equals the output, which is B, over the input, which is E, right? So I'm just expressing this in terms of B. This function right here, A, is going to be this transfer function times this transfer function times this transfer function for the same logic. So again, A, and just to write it this way, is going to be, I'm going to go backwards. So I'm going to have 1 over tau IS. This is going to be multiplied by tau DS. This is going to be multiplied by KC. multiplied by this ES term. All right, so now I can add these two things together, simplify, rearrange, and calculate the overall transfer function for this process. So we can get the transfer function fairly easily if we have this logic flow or this block diagram that tells us the logic and how information transfers through the system. And this is sort of an example of what we do for PID control, but this here in itself is not actually a PID controller. And this tells us the algebraic solution for that example. Okay. I think the last thing we want to talk about today is if we have nonlinear processes. I already told you if the process is nonlinear, the first thing we can do is you can use equation 5.7.3. Nonlinear process, use that. And we can derive the transfer function. Other things we can do is we can linearize nonlinear terms and then go through and derive the transfer function. So the way that we linearize nonlinear terms, and I'll just kind of tell you that, yes, this is something that I would like you to be able to do. And I would like you to be able to do this only for a couple of specific types of terms, but I'll show you on the next slide. So linearization of a nonlinear term is done using Taylor series. And we only care about Taylor series up to the first term. So we'll take, we can approximate the function by taking the value of the function at the initial condition minus, we are taking the Taylor series around the initial condition. So again, that would be x naught. So we'll take the Taylor series around that case. And it looks like this. And I'll do a quick example on the next slide. So the approximation of the function is the value of the function at the initial condition plus the x minus, so this is the linear term, times the derivative of the function evaluated at the initial condition. Okay, that's maybe saying that in words. So an example of a nonlinear term could be an exponential, so exp to the negative e over rt. So this is like a reaction rate term. So if we want to take a Taylor series approximation for this term, the Taylor series, so what I do is I evaluate this term at the initial condition, or where I'm taking the Taylor series around. So this is going to be exp of e over rt0. So that's the first term, plus I have t minus t0, right? So this telling us t minus t0 right here, times the derivative of the function around x naught. So now I have to take the derivative of this term, and then I evaluate it at t naught. So I'm just going to tell you what this is. So the derivative of this term is going to be e over r t naught. So the derivative of the exponent is you have to do the chain rule. So it's going to be the exponent. So it's going to be e exponent of this term times the inner derivative, which is going to be let's see. So okay, well, I'll just give, you can go back and look at the derivative for this. So the e over rt naught and then multiplied. So this right here times exponent of the same term e over rt0, because we take the derivative and we evaluate it at the initial condition. So this is the derivative evaluated at t naught for this term, and then multiplied by the linear term. The only other function, so in the exponential terms, the other function that might be useful, and so maybe this might show up later. So on your own, practice do the Taylor series of the function square root of L. So again, we can approximate this as the first term is going to be the square root of L naught plus something else. So this right here is something that maybe you can practice, and maybe this will come back to this one later. So square root exponential functions, those are common functions that are going to show up in process equations. And then the other equation that shows up in a process equation, the other equation that might show up is going to be, actually, if I go back to here, I think this should be a t squared, because the derivative of 1 over t would be 1 over t squared. So this should be r t naught squared. I think I forgot that square term. Anyways, go ahead and check this for me, and let me know next time if I have an error here. Okay, the last thing that we will need to do to linearize could be a bilinear term. So this would be essentially, we have a flow that's a function of time, and we have a temperature that's a function of time. And for example, if this is the input, this is the output, multiplying these two things together is a nonlinear term. The approximation for f times t, and then you can maybe show this to you can prove this to yourself. So it's the function evaluated at the initial condition plus f naught times t minus t naught. So we have the linear term for the temperature plus t naught times f minus f naught. All right. So this is the approximation here. So those are the three terms that I think that you should be able to know how to linearize that might show up later. So maybe just look at those or practice those. So I'm going to stop there for today. That kind of gets through. This slide just shows a little bit of an overview. I'm going to